Today we're going to look at some of the other segments that we might deal with in circles. So not just a radius and diameter, but some additional segments and some additional properties that those will help us figure out in diagrams and solve some problems. So the parts of the circle we're looking at today, we start with what we know, diameter and radius. So again, we know the diameter is always going to go all the way across a circle. It's always going to be a segment that also goes through the center of that circle. So in the diagram we have to the left, we have, and actually let's label the circle, okay. We have our center point V. So we would probably call this circle V for the center. And so usually when we name circles, we do name it by the center rather than all the extra letters that may be labeling points around that circle. And so our diameter has to go through that center V. What's the only segment that goes through that? Again, segments always use two letters, so we would name that as segment CF. So again, it is a segment. Its endpoints are on the edge of the circle. So the radius, we actually have two radiuses, or specifically radii. So if you hear me use that word radii or see that written, it's just plural of radius. So we have two radii on here because we have a center and we go each direction out from the center out to the endpoints of the diameter. So we're looking at segment CV or VC, wouldn't really matter which one. And we also have VF. So those are both radii. They both go from the center out to the edge. And so thinking back to our definition of circles that we looked at last time, the loci of all points equidistant from the center, technically, every single radius that you could draw in a circle is always going to compare how to the other radii? Well, they're always going to be congruent. Alrighty, so a chord, this is a new one. A chord is any segment anywhere that has its endpoints on the edge of a circle. So technically, the diameter that we just used is a chord. So let's write that down as one of our possibilities. So we could use diameter CF, but we have other segments as well. So again, we could do segment ZA. And again, I know that's a segment with the way I'm writing it out because it doesn't have any arrows on the end of that small picture right on top of the name. Do we have any other chords that we could put in there? Actually, those are the only two. So just two, CF and ZA. So again, endpoints have to be on the edge of the circle. So the difference between a chord and the next one, a secant is always going to extend past the edge of the circle. So in other words, I could use line ZA. And again, don't forget the way to change that notation is just put arrows instead of like a little picture of a line up top instead of just a segment that stops. Let's see here. And that is actually the only line that goes straight through the circle and intersects it in two places, 2 points on the edge. And so our last term is tangent. So a tangent is going to be a line or a ray, but it's only going to intersect the circle at one place. And so we actually only have one tangent in this diagram. See if you can find it. Okay, the only place that only hits once is at point B. So BH, which is drawn as a ray, so it only has the one arrow on it. Now, another thing that actually is a property of all tangents is when they're drawn, and let's go ahead and kind of test this out by sketching it, it's always going to be perpendicular to the diameter or the radius at that point. So let me go ahead and sketch in, let me connect point V and B. So if I draw in a line there, it does look indeed like it is perpendicular, like it makes a right angle. So let's go ahead and draw that in at B. So angle VBH is 90 degrees. So let's actually write that in. So angle VBH equals 90 degrees. And if we were actually to construct this with a compass and straight edge, basically you could just draw the circle and then pick one random point. You should be able to draw a line or a ray that only touches at that point. It's just going to barely skim the edge of the circle. Alrighty, so take a moment if you need to, pause the video if you're not working off a printed copy of notes, because I would absolutely at least draw out a circle and label the different pieces. Although best would be go ahead and write out all your definitions. Okay, so let's apply some of these. The first thing is just looking at the lengths of any segments, any chords, any rays, and how they interact. So our first one, example 1, find the length of dt. So segment dt is this guy. Now, are there any other shapes that you can see in the diagram? Well, wait a second. I have a right angle at A. I have a triangle, so I know this is a right triangle. So anything I know about right triangles, I could use. So I could use Pythagorean Theorem. I could use SOHCAHTOA. However, do I know anything about radius AT? Well, wait a second. If AT is a radius, then isn't DA a radius? So that means, how do they need to compare? Well, they have to be congruent. Every radius is congruent to every other radius in the circle. And so now I actually have a right triangle. I'm looking for segment DT, so let's go ahead and label him as X. And now I can just approach this as I would any other right triangle problem. I have 2 of the sides. I'm looking for the third side. So what's going to be best, Pythagorean Theorem or SOHCAHTOA? Now let's try Pythagorean Theorem. That one should work. So we have our 2 sides. A squared plus B squared equals C squared. Our A and our B, our legs are both 5. And our hypotenuse is X. And then I just solve for X. So 5 squared is 25. And 25 plus 25 is 50. And so I need to take the square root of both sides to solve out for the X. So X equals the square root of 50, except I do want to go ahead and break that down. Always better to give reduced radical version. 50 we just did was 25 times 2, and 25 was that perfect square. So I can simplify this out to 5 root 2, and that's equal to X, otherwise known as segment DT. All right. So examples 2 through 6, excuse me, I mislabeled that. I'll fix that on the copy that I post online. This should actually be 2 and 3. So just the 2 examples that are below. So I'm actually going to have to reduce the size of my screen a little bit so we can see everything at one go. There we go. So using circle S, we need to complete the questions below. So first thing I'm going to do though, before I read those, is let's look at what we have going on here. I have a couple diameters. I have a bunch of radii, but one of my radii is actually labeled as 10. So I could label every other radius in there as 10. I also have this 60-degree angle. So let's think about this. I have a triangle, 2 of the sides are 10, which makes it what kind of triangle? 2 sides are equal means it's an isosceles triangle. And so I have an isosceles triangle with 60 as one of the angles. Wait a second. So if both of these angles here are going to have to be equal, and everything adds up to 180, what's each one of those angles going to be? Wait a second. This isn't just an isosceles triangle. Each one of these would end up being 60 degrees to add everything up to 180. So that means this is actually an equilateral triangle, which means what's the length of segment DE? Well, that's going to be 10. And every other radius on here is also 10. So we have 10 here and 10 here and 10 here and 10 here. So now let's see what questions they actually wanted us to answer. So number 2, find the length of BF. Well, let's see here. BF is actually what kind of segment? BF goes all the way across the circle. BF is a diameter. Well, if we know that every radius is 10, that means the diameter BF has to be 20. So that's the length of BF. Okay, then find the length of BE. So again, that's a typo. You'll have that fixed in your version. That should actually be finding the length of DE, which we already found. We have that labeled. That's equal to 10. Alrighty, next set of questions. So The rest of our questions are going to use some properties of tangents. Now, we already looked at one really quick. So we already looked at the fact that a tangent is a line or a ray or segment that only intersects the circle at one place. So in our diagram, it intersects, we have one tangent, line M, that intersects at point S, and we have another tangent, RT, that intersects at T. But specifically, we know that a tangent is always going to intersect at exactly one point. So one and only point. And technically we call that the point of tangency. Okay, a line is tangent to the circle if and only if it is blank to a blank drawn to the point of tangency. So let's see, what kind of angle does it make at at point S? Well, it makes a right angle. So one of the ways that we could put that in is actually perpendicular. And we can use our symbol for perpendicular. And it's always going to be perpendicular to a radius that's drawn at that point of tangency. So in this case, S is our point of tangency. And the radius we drew to it, segment AS, well, that's going to be perpendicular to our tangent, line M, or line SR. Okay, tangents drawn to the same circle from the same point outside the circle. So both of these tangents are drawn from point R. And what happens is they are always going to be congruent every time. So let's go ahead and mark that on the diagram. Again, don't forget to mark segments congruent. You typically use a dash mark. So I'm going to use 2 just so it stands out a little bit better. And so it's going to be congruent to just that piece there. Segment SR is congruent to RT. So we could actually write that down. SR is congruent to RT. And so we can use that together with what we know about, having that right angle. We might be looking at a lot of right triangle problems. So we can put those together to solve some problems. Here we go, example 4. So circle P is given, segment PT is 15. So let's label that. Let me switch over to red so it pops better. So there's our 15. RT, that outside segment, technically our tangent, is 24. And RP, so this whole segment here, is 28. We're trying to determine if RP is tangent. Well, RP is not tangent, obviously. RP, no. What was supposed to be in your notes, again, will already be fixed in your version. So let me go ahead and edit that out. Oops. We should be looking at whether or not RT is tangent, and that's what you're going to have in your printable copy. So if that was tangent, then that means which angle would have to be our right angle? Well, that would have to happen at T. So if T is our right angle, then what test do we know for testing whether or not things make right triangles? Well, Pythagorean Theorem would tell us whether or not that works. And so which side on our triangle would have to be the hypotenuse to put into that C spot? Well, that would have to be 28. So a squared plus b squared equals c squared. We need to test, is 15 squared plus 24 squared equal to 28 squared? And so let's test that out. Let me grab my calculator. We've got 15 squared. Well, that's going to give us 225. We have 24 squared. That's going to give us 576. And 28 squared gives us 784. So if 225 plus 576 adds up, then we're good to go. So 225 plus 576, that gives me 801, which is not equal to 784. So unfortunately, RT is not tangent. It doesn't quite make that right triangle. So keep that in mind. If you're asked that question, whether or not it makes a right triangle, again, plug it into Pythagorean Theorem like we did back in our right triangle unit. Okay, example 5. If JK, what we have labeled as X, is tangent to circle L, then we're going to solve for that length X. Okay, but we have a few pieces of info here. So I'm seeing I have an 11 labeled and I have a 7 labeled. And that 7, well, wait a second. Definitely not the same length as the 11. So I'm thinking that that 7 only goes to this piece. So that means I still need the interior segment of my circle. What do I know that has to be? Well, that's a radius. And you already have segment JL, the 11, labeled as a radius as well. So if that piece is also 11, that means that entire segment LK is 18. And so again, if this were a perfect tangent, if JK was a tangent, what kind of angle would we have to have at J? Well, we'd have to have a right angle. So that tells us what we have to plug into a Pythagorean theorem to figure out that extra value for x. So x and 11 would be our two sides. So x squared plus 11 squared would have to equal the 18 squared. So multiplying that out, well, 11 squared is 121. 18 squared, I got to check that. So 18 squared is 324. Next step, yep, move the 121. So subtract that from both sides. That will give us 203. And then we take the square root of that. So square root of 203. And I'm going ahead and figuring out that actual square root because I know that 203 is not a perfect square. It's definitely not on the possible lists that I'm aware of. And 203 doesn't look like it's going to have any really good factors to it. We could absolutely test it out with, factor tree, and I believe that one comes out prime. And so the most exact we could get is either leaving it a square root of 203 or rounding it off to our decimal, which would be about 14.25. And didn't specify which way to leave it, so either one of those would be a valid solution. All righty. Example 6. So A and C are points of tangency. Find x. So this one, if A and C are both tangency points, and they both go out to segment B, well, what needs to be true about those two segments according to the definition that we just had at the top of the page? Well, any two tangents drawn out to the same point are always going to be congruent to each other. So that means we can do 8x minus 19 equals 5x plus 23. The problem is just asking us to solve for x, so two-step equation, and we're there. So let's go ahead and combine our x's first. I'm going to subtract a 5x from both sides, so that leaves me a 3x minus 19 equals 23. Okay, then add 19 to both sides. So 23 plus 19 gives me a 42. And divide both sides by 3. 42 divided by 3 gives me 14. Again, wouldn't be a bad thing to check your work to plug in your 14 to both of those expressions, and they should come out with the same value. Okay, example 7 looks a little convoluted, but let's go through. Let's see, find the radius of circle Q. Well, let's think about this. So circle Q, one of the radii would be like this guy. So let's go ahead and mark that as x. And for them, it looks like we have a whole bunch of extra information in here, but let's just try and look at this selectively. So I'm actually going to go ahead and just look at one side of this at one time. So let me go ahead and cover up the left-hand side of my diagram. So what kind of figure do you see now? If you ignore the circle, we've got a right triangle, and it looks like I have two possible sides, one that I need to solve for, one that I know, and I have an angle. So wait a second, let me actually draw this out. So if I think of this as a triangle here, and we have our right angle, we have our x that was touching the right angle, we have the 50 on the other side, and we have an 18 degrees here. What technique do you think we're going to need to use? So I can't use Pythagorean theorem on this. The only other technique that we practiced with right triangles was actually solving with trigonometry, so SOHCAHTOA. So that's what we're going to do. So let's go ahead and set this up. I'm going to change over to red. So compared to my 18, what kind of side is the x? Well, he's an opposite. What kind of side is the 50? He's a tangent. Excuse me. My brain is getting ahead of me. He's adjacent. Opposite and adjacent use which ratio? And again, if you need to, SOHCAHTOA as your reminder. Or again, don't forget, that's one of the things that's on the formula sheet. So we'll be providing that for you on your test. And so let's go ahead and use our tangent equation then to write that out. So tan of 18 degrees equals x over 50. And so to get the x by itself, just multiply both sides by 50. So 50 times tan of 18 degrees equals x. Don't forget, before you actually plug in your calculator for any SOHCAHTOA problems, you need to check your mode. Make sure you're in degree mode, especially if you're using a TI calculator for your calculations. So let's see, I'm in degree mode, so I can just type it in exactly as is. So 15 tan of 18 degrees, and I'm getting out that x is approximately equal to 16.25. And I'm going to go ahead and write in my feet, because my units feet, because they gave me that in the problem. All righty, last example, I believe. Yep. So example 8, find the perimeter of triangle DEF. So we have two properties that we could use. Either tangents are always right, make right angles with the radius, or they're congruent if drawn out to the same point. Now I don't have any radius drawn on here or radii drawn on here, so I think I'm going to have to use that second rule that all of my lengths on the outside are equal. So again, let me look at this selectively. So first thing is, let's look at that very right-hand piece. So we have a 16. Do we have another segment that would have to be congruent to that? Yeah, well, we have the other tangent that's drawn to that same point E is going to be congruent. So that means we're going to have a 16 on that section. All righty. So I can actually use that all the way around my circle. So our segment DG11, which one should that be equal to? Well, that should match up with DH. And then how about the 9.5? Well, that should match up with segment GF. And so when it's asking us to find perimeter, what's perimeter again? We did that in a review problem. Yeah, perimeter is when we add up all the sides of the figure. So that means we just need to add together all of the lengths that we have. So we're going to have 11 plus 11. We're going to have 16 plus 16. And we're going to have 9.5 plus 9.5. And all of those added together will give us our perimeter. Alrighty, so 11, another trick that I could do, because I know each one of these values is used twice, I could just add them up and then multiply by 2. So either way that you approach it, we should get that the perimeter equals 73. Alrighty, as always, let me know if you have any questions. And if not, if you feel ready, your next activity is to work on your practice quizzes. Talk to you later.